Let's continue taking a look at the foundational ideas that led to the development of quantum mechanics. And at the start of this lecture, I want to take a look at something now called at least, the Compton effect. It's called the Compton effect because the explanation for it was derived by an American physicist by the name of Arthur Compton. For his work in this study, he received the Nobel Prize in Physics. Now, what is the Compton effect? And the Compton effect sounds similar to the photoelectric effect. If you'll recall, the photoelectric effect involved a photon striking an electron and knocking that electron free at the cost of having all of its energy absorbed by the electron. So some of the energy of the photon went to freeing the electron, and then the remaining energy of the photon went towards giving that electron kinetic energy. Now, the Compton effect is a little bit different. It involves typically photons with noticeably shorter waves than the photons required to activate the photoelectric effect. In fact, these waves tend to be so short that they are in the X-ray part of the spectrum. And instead of being completely absorbed by the electron, in the Compton effect, a photon strikes an electron and some of the energy of the photon is transferred to the electron. So this is going to be a little bit different. The photon survives, but it does so at the cost of some of its own energy. Now, what happens in the Compton effect is that by losing energy, the photon, which goes as hf, the frequency also goes down, and if the frequency goes down, the wavelength increases. The thing is, when this observation was first made, Maxwell's theory said that the wavelength and the frequency should not change, that a ray of light should just bounce off an electron and be unaffected, except maybe in the fact that it's now a reflected ray of light. But the expectation that the wavelength would change upon this reflection or scattering was completely unexpected. Because these wavelengths are typically so small, the effect is relatively noticeable. Sometimes the Compton effect can happen with photons with a larger wavelength, but the change in wavelength from before to after is still going to be pretty small. On the scale of things, the change of wavelength is not that significant for ultraviolet light. It only becomes noticeable when you start talking about the very short wavelengths of X-ray light. Because of the relatively more extreme energies involved in the energy gained by the electron, we have to use relativity. And I'm not going to derive the Compton effect via relativity, but I want you to be aware that what Compton did not only involved a quantum mechanical idea of photons, but it also incorporated relativistic ideas in order to fully come up with the equation that describes this effect. So what we have, and let's just make sure we understand what's going on in this setup. We have an incoming photon and an electron that is relatively stationary. The incoming photon strikes the electron, and the photon scatters off at some angle, and the electron is moving off in some direction after the collision. We are often concerned with the angle of the photon after the collision compared to the incoming angle of the photon. And these things can be measured. There are plenty of detectors. An X-ray detector is nothing too sophisticated even 100 years ago. What Compton found was that there would be a change in the wavelength. And he was able to derive an expression for by how much the wavelength of the photon changed from after the scattering with lambda final to the wavelength before it struck the electron, lambda initial. And he found that this difference in wavelength was equal to h Planck's constant divided by the mass of the electron times the speed of light, and then times the quantity 1 minus cosine theta, where of course theta is the angle between the outgoing photon and the incoming photon. It turns out that because theta is always between 0 and 180 degrees, that cosine theta is always between 1 and negative 1. Now, if theta is 0, we have cosine of 0 is 1, we get that there's no change in the wavelength. It's like the incoming photon just skips over the electron. The other extreme is if the photon bounces immediately backwards. If theta is 180 degrees, cosine of theta is negative 1, we get 1 minus negative 1 is 2, and so the maximum possible change in the wavelength is 2 times h over the mass of the electron times c. And that maximum possible difference is on the order of about 10 to the negative 12 meters. So if the wavelength of an ultraviolet photon changes by 10 to the negative 12, considering that an ultraviolet photon might have a wavelength of 10 to the negative 8, a change on the order of 10 to the negative 12 is like 1/10,000th, and we're not going to notice it with the ultraviolet photon. But if it's an X-ray photon that is already with a wavelength of about 10 to the negative 12, a change in the wavelength on the order of 10 to the negative 12 meters is quite a noticeable effect. So the Compton effect is a relevant thing when you start getting into short wavelength light like X-rays. Let's consider such a situation. We have a photon that has an initial wavelength of 5.38 times 10 to the negative 12 meters, and it scatters off of an electron, and its new wavelength is 5.63 times 10 to the negative 12 meters. Through what angle did the photon scatter? What's its outgoing angle compared to its incoming trajectory? And the change in the wavelength, lambda final minus lambda initial, notice that both values are times 10 to the negative 12. So we can simply take 5.63 minus 5.38 and multiply that result by 10 to the negative 12, and we get 2.5 times 10 to the negative 13. Now, this quantity is going to be equal to h over mc times 1 minus cosine theta. We're trying to find theta. So we got to do a little bit of algebra. But if we go through all of that, what we get is that theta is going to be equal to the inverse cosine of 0.897, and that winds up being 26.2 degrees. So we got an answer between 0 and 180 degrees. That's what we're looking for here. And as it says in the text near the bottom, you cannot get a wavelength that changes by more than 4.85 times 10 to the negative 12 meters. That is the absolute limit of 2 times h over mc when you use the mass of the electron. So it is something that happens only on the scale of X-rays, but when the physicists of the time discovered this effect, they couldn't explain it until Compton came along and showed not only that quantum mechanics and this idea of photons is correct, but so is relativity. Now the last big pre-quantum mechanics observation that I want to discuss is, as you can see, called atomic spectra. In the graphic on the right, you see this graphic labeled emission spectra, and you see this rainbow at the top of the heap called continuous spectrum, and then you start seeing different spectra for very particular elements: mercury, lithium, cadmium, so on and so forth. Hydrogen at the bottom. When you take an element and you get the atoms into gaseous form, and then you place it into a tube and you electrically excite the atoms in the tube, they will start to glow. But the thing is, they will glow with very characteristic signatures, and they will emit only the very particular wavelengths of light. So what you see on the screen are the emission spectra for different elements. And as you compare mercury and lithium and cadmium, for instance, with the other elements that you see on the screen, potassium is quite remarkable, but with the other elements you see on the screen, you can see some very clear differences between one element and the next element. And in fact, it's this observation that allows us to determine what elements are in the atmospheres of planets that we've never come close to, of even stars themselves. In fact, it was this observation like this that allowed us to discover the element helium before it was discovered on the Earth. They found this characteristic signature for an apparently unknown element emitted from the sun, and they decided that this had to be something characteristic of the sun, and so they gave it the name helium after the Greek sun god Helios. Of course, subsequently they found it on the Earth, but there's the name right there. Why elements would behave this way was just one of those mysteries in the late 19th century. Maxwell's theory said that these emission spectra should all be pretty much like rainbows, that there would be a continuous spectrum of frequencies emitted. And why it was just these very characteristic ones was a mystery. In order to start getting to the bottom of this mystery, let's just focus on the simplest element. If we can figure out the simplest element, then we might be able to come up with an explanation that we can extrapolate to the more complicated elements. Hydrogen is the simplest element. Its nucleus consists of a single proton, and it is orbited by a single electron. When you look at electrically excited hydrogen gas, and you will see kind of the purplish emission, a light purple that you see in the figure on the far left. That vertical light purple line is hydrogen gas being electrically stimulated. But if you pass that light through a diffraction grating, you will see very characteristic and well-separated wavelengths. There's a red wavelength, there's a blue wavelength, and you can see a faint violet wavelength. There are actually two there. These are always emitted by electrically excited hydrogen atoms. It's always the same, and just completely baffles Maxwell's theory. With these easily measured wavelengths, the diffraction grating allows us to determine these wavelengths with great precision. In 1885, a Swiss teacher by the name of Johann Balmer noticed a pattern in the values of the wavelengths that he saw for hydrogen. And he developed an empirical formula, just a way of calculating these wavelengths based on very simple input values. And later, it was found that hydrogen emitted other kinds of light, non-visible types of light, that could also have empirical formulas for their very particular wavelengths. Theodore Lyman discovered ultraviolet radiation from hydrogen atoms. You had other European and American scientists, Friedrich Paschen, Frederick Brackett, August Pfund, Curtis Humphreys, finding emission spectra from hydrogen in the infrared part of the spectrum. So from the ultraviolet part of the spectrum into the visible part of the spectrum into the infrared part of the spectrum, hydrogen is emitting very particular wavelengths of light. Now, just for the sake of you moon buffs out there, if you look at the moon from an angle we wouldn't normally see it, I believe that this is from examining the moon from the moon's south pole. We don't normally see it from this side. You can see some different pattern of craters than you would normally see, and some of those craters have been named after Lyman and Balmer and Brackett. The formulas derived by Balmer, Lyman, Paschen, Brackett, etc., were compiled into one grand unified formula in the very early 1900s by another European scientist, Johannes Rydberg. And in this one formula, he basically says you can predict the wavelength lambda by first saying 1 over lambda equals 1.097 times 10 to the 7 inverse meters times 1 over n final squared minus 1 over n initial squared. And n, whether it's n final or n initial, is simply a positive integer where n final is less than n initial. When n final is equal to 1, you reconstruct the wavelength discovered by Lyman. When you have n final equals 2, you reconstruct the wavelengths of visible light. When n final equals 3, 4, 5, 6, you recover the infrared wavelengths discovered by the other scientists that we've discussed. So it's a very good formula for all sorts of different wavelengths emitted by hydrogen, whether it's visible light, ultraviolet light, infrared light. And this formula is very accurate. The question is why, but it does a pretty good job of allowing us to figure out these wavelengths. So this only applies to hydrogen, but if we can figure out how it applies to hydrogen, perhaps we can figure out what's going on with the other elements. Now, just to show you some of the details of the Rydberg formula, recall that the n final equals 1 would give us the Lyman series, n final equals 2 gives us Balmer, n final equals 3, Paschen, so on and so forth. The shortest possible wavelengths will occur when n initial equals infinity. If n initial is equal to infinity, you have 1 over infinity squared, which is basically 0. And what you wind up getting is that the shortest possible wavelength of light emitted in the ultraviolet part of the spectrum is 91.2 nanometers. You will simply not see a wavelength of light emitted by hydrogen with a wavelength shorter than 91.2 nanometers. In the Balmer series, the absolute minimum possible wavelength would be 365 nanometers. In the Paschen series, it would be 820 nanometers, so on and so forth. Let's do a little calculation in the Lyman series. What are the 4 longest wavelengths of light emitted by a hydrogen atom in the ultraviolet part of the spectrum? Now, ultraviolet means Lyman series. We are restricted to that because that is the only series that gives us the ultraviolet light emitted by hydrogen. The Balmer series gives us the only light emitted in the visible part of the spectrum. But then there are the several other types that give us wavelengths in the infrared part of the spectrum. But ultraviolet emission by hydrogen is Lyman series, and n final equals 1. Visible light emission by hydrogen means the Balmer series, and it restricts n final to be 2. First problem here is ultraviolet light, so n final equals 1, and we want the next 4 longest wavelengths. So the longest wavelengths occur when n initial is as close as possible to n final. The shortest wavelength, we chose n initial equals infinity. The longest wavelength, we want the smallest possible value of n initial. But I can't let n initial equal n final. N initial has to be greater than n final. So the nearest n initial that I can use in this problem is n initial equals 2. And then for the next subsequent longest wavelengths, n initial equals 3, n initial equals 4, n initial equals 5. We plug in for n initial equals 2, 1.097 times 10 to the 7 times 1 over 1 squared, because n final equals 1, minus 1 over 2 squared. That gives you 8.228 times 10 to the 6, and then don't forget to take the inverse. 1 over 8.228 times 10 to the 6 is 1.215 times 10 to the negative 7, which is meters, which is equivalent to 121.5 nanometers. And that is definitely in the ultraviolet part of the spectrum. You should be able to reconstruct these calculations on your own and get that lambda 3 must be 102.6 nanometers, lambda 4 must be 97.2 nanometers, and lambda 5 must be 95.0 nanometers. You can see that as n initial goes up for a constant n final, that the subsequently calculated wavelength goes down. These are all in the ultraviolet part of the spectrum, so this is definitely Lyman series stuff. If it were in the visible part of the spectrum, you would find things between about 370 nanometers and 750 nanometers. Now, like I said, this business with atomic spectra was one of these mysteries. And the solution to this mystery was first divined by the Danish scientist Niels Bohr, who was an exceptionally remarkable scientist in his ability to form a school of thought in which other scientists were able to make some very profound and fundamental discoveries. In fact, Niels Bohr's own son won the Nobel Prize in Physics in the 1960s. There's a story that was told about him when asked why is his school so successful. He said, well, it's because I'm not afraid to confess to my students that I'm a fool. That story kind of charmed some of the European scientists at the time, and one of the great scientists in the Soviet Union of that era, by the name of Lev Landau, ran his own successful school. And one of Landau's top students was one time giving a speech, and he was talking about the success of the Landau school, and unfortunately it appeared that he kind of mangled Bohr's statement. Lifshitz credited the success of Landau's school by saying that Landau was never afraid to confess to his students that they are fools, although some people rightly noted later that that really was the fundamental difference between Bohr's school and Landau's school. Coupled with this business of atomic spectra was the knowledge that the structure of the atom kind of defied explanation. In the first decade of the 20th century, a New Zealand physicist working in England by the name of Ernest Rutherford, along with his graduate students, discovered the structure of the atom, that there was this small, densely packed, positively charged nucleus, and about it orbited the negatively charged electrons. Of course, a negative charge is attracted to a positive charge. So this is perhaps okay for gravity. The planet Earth is attracted to the sun gravitationally, and yet the Earth doesn't spiral into the sun because the gravitational force is kind of on the weak side. But pound for pound, if you'll pardon the metaphor, the electromagnetic force is a lot stronger than the gravitational force. And the expectation is that the electrons will spiral into the nucleus in about a nanosecond. So if we wait about a nanosecond and see what happens to the atoms in you, and I guess a few nanoseconds have gone by, we might notice that the atoms in your body, the electrons in your body, have not collapsed into the nearest nucleus. You still have your atomic structure, at least I hope so. Maxwell's theory can't explain that. Maxwell's theory says this negatively charged electron will spiral very rapidly into the positively charged nucleus, and the Rutherford model just can't be true. But the Rutherford model is experimentally verified, and where you see the experiment and the theory in contention with each other, you got to take the side of the experimental results. Now, Bohr knew about Rutherford's results, and Bohr knew about this business with atomic spectra. And what Bohr did was he did not answer the question about why the nucleus, or why the electron doesn't spiral into the nucleus. But he did shift the goalposts in terms of what needs to be explained. He was very aware of the developments in blackbody radiation and the photoelectric effect of how the photon was getting quantized. And he applied that general philosophy to the situation of the electron orbiting the nucleus in the hydrogen atom. So if light could be quantized, Why not electrons? And this sounds like a tautology because electrons are already particles. They are already coming in these quantified, discrete particles. They are not, how can you quantize what's already quantized? And Bohr said, I'm not going to quantize these particles. Nature's already done that for me. But there are certain dynamic properties that the particle can have, and I'm going to assume that these dynamic properties are quantized. And Bohr ultimately came up with saying, okay, we have this electron orbiting in a circular path about the nucleus. This electron has mass, it is moving in a circular path. We can say it has angular momentum. But what Bohr did was he said this angular momentum is quantized. It could have this value or that value, but it cannot have a continuous set of values between those extremes. And he went further, and he came up with a formula for this quantization, this quantized angular momentum. He said that the angular momentum can adopt values that are equal to n times h over 2 pi, where n is a positive integer. In quantum mechanics, h over 2 pi occurs with such regularity that it's given its own symbol, h bar. And so Bohr said the angular momentum of an electron orbiting the hydrogen nucleus is quantized in values of n times h bar, integer times h bar. By doing this one bit, he managed to combine the two issues of atomic spectra and the Rutherford model of the atom, took these two seemingly separate problems and showed that it can be condensed down to one problem. Now, the one problem is, why is the angular momentum quantized? But if you can explain why the angular momentum is quantized, then you've explained the issues with the Rutherford model, and you've explained the issues with atomic spectra. So, in a way, this was a unified theory. It's a unification of two seemingly separate problems into one problem. We've seen examples like this in the 1600s. We had the Galilean theory of motion for objects on the surface of the Earth. We had the Keplerian theory of motion for the planets in the heavens. And Newton came along and said, hey, this business with Galileo and this business with Kepler, they're basically the same force. And he came up with his laws of motion and the law of gravity and all of that good stuff. Similarly, Galileo had his theory of ordinary motion, if you will, and James Clerk Maxwell had his theory of electromagnetism. And Einstein showed that the motion of ordinary objects, when they were sped up to speeds like you see in electromagnetism, obeyed some of the properties that had been assigned strictly to electromagnetic effects. And this was Einstein's theory of special relativity. And still later, Einstein took his own theory of special relativity, and he took Isaac Newton's theory of gravity and unified the two into a general theory of relativity, which we still use nowadays. But back to Bohr. If you say that the angular momentum is quantized, one of the conclusions that you are forced to have is that the radius of the electron's orbit about the proton is also quantized. With a little bit of math, you can show that the radius is equal to n squared times h bar squared over mass of the electron times the electrostatic constant of the universe times the charge of the electron squared. So, very strict values for the radius. I can have the radius at one location, I can have the radius at another location, but not anywhere in between. The expression h bar squared over mke squared, those are all constants, and when you calculate that formula, You get that all those constants combined together to create the quantity 5.29 times 10 to the negative 11 meters. In the Bohr model of hydrogen, the smallest value of n is 1, and so Bohr said the radius of the n equals 1 orbit is 5.29 times 10 to the negative 11 meters. And that quantity is called the Bohr radius of hydrogen. Any subsequent radius is equal to n squared times the Bohr radius. And not only did Bohr find that the radius was quantized, he also found that the energy associated with the nth orbit is also quantized. And what he found, again, with a formula that involves things like the mass of the electron and the electrostatic constant of the universe and h bar and the charge of the electron, was that it would be equal to negative 2.18 times 10 to the negative 18 joules over n squared. The overall energy is negative. This is due to the fact that the electron is attracted to the proton. I would have to add energy to the system to free the electron to the point where it has zero energy. It is not at all associated with the positively charged proton. So if I have this electron confined to the region around the proton, there's got to be negative energy associated with it. And that's what Bohr found, negative energy. But he also found that as n got larger, the radius of the orbit got larger, and the energy got closer to zero. And you can imagine that if n is equal to infinity, the electron is infinitely far away from the proton, and the energy of the electron is zero. Now, what does this n really mean? And I'm not going to tell you. Take care. Bye-bye.